More than 70% of our universe is made up of something so strange that it continues to confuse scientists. We still lack a solid understanding of what it is. Dark energy is the term we've given to this mysterious thing, though it doesn't truly describe what it is. It's one of the biggest mysteries remaining in our universe, and solving it could change our understanding of physics forever. Since the Big Bang, our universe has been expanding, with space itself stretching and pushing galaxies farther apart. For a long time, physicists believed that the energy helping this expansion would eventually run out, causing the expansion to slow down. However, a Nobel Prize-winning discovery turned this idea on its head. It says that the universe's expansion wasn't slowing down. In fact, it was speeding up. Scientific communities began to wonder, what could be causing this accelerated expansion? The mysterious force behind this was named dark energy. Yet, giving it a name doesn't explain what's really driving this acceleration. Like dark matter, which makes up 25% of the universe and is also not fully understood, dark energy seems to defy the laws of physics as we know them. It behaves in ways that our current models cannot explain. As the universe expands, it seems that more dark energy appears, almost as if something is coming from nothing, which challenges our understanding. Scientists have proposed various ideas about what dark energy could be, perhaps a new type of particle, a strange liquid, or even an unknown force. But so far, no single explanation has fully accounted for this cosmic mystery. What we do know is that dark energy makes up about 70% of our universe, and its influence is deeply tied to the universe's formation and evolution. In the early 20th century, astronomers discovered that the universe is expanding. They expected that the gravitational pull of all the matter in the universe would slow down this expansion over time. However, as we discussed, later on scientists found expansion of the universe was speeding up, not slowing down. One leading idea is that dark energy could be a property of space itself. According to Albert Einstein's theory of general relativity, space has its own energy, and as space expands, more of this energy is created. This energy could be responsible for the accelerating expansion of the universe. Another theory suggests that dark energy might be related to a new unknown type of field or particle. Some scientists propose that it could be connected to the so-called cosmological constant, a term Einstein originally introduced but later abandoned. The cosmological constant is a fixed energy density filling space uniformly, causing the expansion of the universe to accelerate. A third possibility is that our understanding of gravity is incomplete. Dark energy might not be a separate force at all, but rather a sign that we need to revise our theories about how gravity works on a cosmic scale. Despite these theories, dark energy remains difficult. What we do know is that it's not something we can see or detect with traditional methods. It doesn't emit light or radiation, and it doesn't interact with matter in the usual ways. Instead, we infer its existence from the way it affects the expansion of the universe. As the universe expands, dark energy continues to push galaxies apart at an ever-increasing speed. If dark energy continues to dominate, the universe could keep expanding forever, growing colder and emptier as galaxies move farther and farther apart. In such a scenario, stars would eventually burn out and galaxies would become dark void of space. Some scientists have even speculated that if dark energy's effects grow stronger over time, it could eventually tear galaxies, stars, and even atoms apart, a fate known as the Big Rip. However, this is just one of many possible outcomes, and much more research is needed to understand the true nature of dark energy and its impact on the cosmos. So dark energy remains the biggest cosmic secret in physics. However, with all these great scientific minds across the world on figuring out what this is, it might not be long before we finally find something about this mysterious energy. The one person who comes up with an idea about what this is could be the next Einstein. When we look around, everything we see and touch is made of matter. Tiny particles make up all the things we interact with, and over billions of years, these particles have come together to form galaxies and stars. They all follow the same physical laws and exist within the same space-time framework. But there was a time when the universe didn't have anything at all. So where did all this matter come from? While it might seem like everything had to come from something, scientists also consider the possibility that it all came from nothing. But what does nothing really mean in science? To answer what was there before the beginning of the universe, we first need to understand how the universe was exactly created from what seems like nothing. One of the main ideas in modern cosmology is the Big Bang Theory, which explains how our universe began and evolved. Imagine every star, planet, and galaxy compressed into an incredibly hot and dense point. Scientists believe this is how everything started about 13.8 billion years ago. Since that moment, the universe has been expanding and cooling. So, how do we know this happened? The Big Bang Theory is supported by a lot of evidence. One key piece is the cosmic microwave background radiation, which is like an afterglow from the early universe. This radiation gives us a picture of what the universe looked like just 380,000 years after the Big Bang. Before that time, the universe was too hot and dense for us to see anything. This radiation was accidentally discovered in 1965 by Arno Penzias and Robert Wilson. Another important discovery is the redshift of galaxies. This shows that galaxies are moving away from us, proving that the universe is still expanding. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it seems to be moving away from us, supporting the idea that the universe was once much smaller, hotter, and denser. The Big Bang Theory also explains why the universe has certain amounts of light elements like hydrogen, helium, and lithium. These elements were formed in the first few minutes after the Big Bang, when the universe had cooled enough for protons and neutrons to combine and form nuclei. However, the Big Bang Theory also leaves us with big questions. For example, it doesn't explain what happened before the Big Bang or what lies beyond the part of the universe we can see. It also introduces the idea of cosmic inflation, a rapid expansion that happened right after the Big Bang. This concept helps solve some problems with the theory and matches what we observe in the cosmic microwave background radiation. Before the discovery of the cosmic microwave background radiation, there was a popular idea called the steady-state theory. This theory suggested that the universe had no beginning or end, and that it stayed the same overall, even while expanding, by constantly creating new matter. This theory was popular in the 1940s but lost support when scientists discovered the cosmic microwave background radiation in 1965, which strongly supports the Big Bang Theory. Other ideas, like the cyclic model, suggest that the universe goes through endless cycles of expansion and contraction. These theories are still being explored and developed, adding to our understanding of how the universe began. After the Big Bang, the universe expanded and cooled. In the beginning, it was a hot, dense soup of particles. As it expanded, it cooled down, allowing particles to come together and form the first atoms. These atoms then formed the first stars and galaxies. The universe's expansion continues today, with galaxies moving away from us in all directions. Let's think even further back. The first long-lasting particles, protons and neutrons, appeared around 1/10,000th of a second after the Big Bang. Before that, there wasn't any material as we know it, but physics lets us trace the timeline even further back to processes that happened before any stable matter existed. This thinking of how the universe was started from nothing also brings to the concept of the grand unified epoch. A likely idea is that the universe was filled with a hot mix of particles, including quarks, which are the building blocks of protons and neutrons. There was an almost equal amount of matter and antimatter. Each type of matter particle, like a quark, has an antimatter counterpart that's almost identical, but with one key difference. When matter and antimatter meet, they destroy each other in a burst of energy, meaning these particles are constantly being created and destroyed. But where did these particles come from in the first place? If we think in terms of quantum field theory, it tells us that even a vacuum, which we think of as empty space, is full of activity in the form of energy fluctuations. These fluctuations can cause particles to appear and then disappear shortly after. This might sound strange, but such particles have been observed in many experiments. The vacuum of space is filled with particles constantly being created and destroyed, seemingly out of nothing. However, this suggests that the quantum vacuum is actually something rather than nothing. Now, let's ask, where did spacetime itself come from? To answer this, we need to go back to the very beginning, into the Planck epoch. This period was so early in the universe's history that our best theories of physics no longer work. It happened only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Usually, physicists use quantum mechanics to understand tiny particles and general relativity for large cosmic scales. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines the two. We don't have a perfect theory of quantum gravity yet, but ideas like string theory and loop quantum gravity suggest that ordinary space and time come from deeper microscopic processes. What we experience as space and time results from quantum processes. Right now, they don't make much sense to us because we are used to the large-scale world. Quantum fluctuations happen constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a brief moment, and then destroy each other. This phenomenon is known as quantum foam. But quantum fluctuations alone don't explain the vast scale and complexity of the universe. There is also dark energy, a mysterious force that fills all of space and accelerates the expansion of the universe. While we don't fully understand dark energy, it's believed to play a crucial role in the creation and evolution of the cosmos. So, how did we go from quantum fluctuations and dark energy to the vast, structured universe we see today? The answer lies in inflation, or rapid expansion, that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded at an incredible rate, setting the stage for the formation of galaxies, stars, and planets. In the Planck epoch, our usual understanding of space-time and cause and effect breaks down. Despite this, all candidate theories of quantum gravity describe something physical happening during the Planck epoch as some quantum precursor to ordinary space and time. But where did that come from, even if causality doesn't work in the usual way? It might still be possible to explain parts of the Planck epoch universe in terms of other parts. Unfortunately, our best physics can't provide clear answers yet. Until we develop a theory that explains everything, we won't be able to give a definitive answer. The most we can confidently say is that physics hasn't yet found any confirmed instances of something coming from nothing. Now, as we understand about the beginning of the universe, we will start exploring what was there before nothing. None of the evidence from the cosmic microwave background radiation or quantum fluctuations tells us what existed before the Big Bang. The Big Bang theory explains that the universe started from an incredibly dense and hot point called a singularity. Think of a singularity as a point where everything we know about space and time breaks down. This singularity raises some big questions. If our usual laws of physics don't apply here, then what are the rules? To understand this, we need to look at Albert Einstein's ideas. His theory of relativity changed how we see the universe by connecting mass and time. According to his theory, time isn't fixed but changes based on the gravitational pull of massive objects. He showed that massive objects, like Earth, can slow down time. Now, if mass slows down time, imagine what the singularity would do, containing all the mass of the universe. It would stop time completely. So, according to Einstein, the idea of before the Big Bang doesn't really make sense because time itself didn't exist. The cosmic microwave background radiation is a key piece of evidence. It comes from a time about 380,000 years after the Big Bang, when the universe was cooling down and forming hydrogen atoms. Before this 380,000-year mark, the universe went through several stages, starting from the Planck epoch to the grand unification, inflationary, electroweak, quark, and hadron epochs. Each stage saw different particles and forces evolving into what we know today. When we talk about the universe at such a small scale, quantum mechanics takes over from classical physics. This led scientists like Stephen Hawking to think about how quantum theory could apply to the whole universe. This is where inflationary quantum cosmology comes in. Unlike classical theories that describe the singularity as a point with zero volume, quantum cosmology suggests there's an element of uncertainty. This means we can't pinpoint the exact moment the universe was created, and particles can appear and disappear from what we call a vacuum. In physics, a vacuum isn't completely empty, but rather a state without particles. According to Heisenberg's uncertainty principle, there's always some level of fluctuation, so a perfect vacuum with zero field values is impossible. The positive energy in stars and galaxies must be balanced by an equal amount of negative energy, like gravity. If the universe's total energy is zero, then it's possible for it to come from nothing. The idea that hundreds of billions of galaxies could come from nothing sounds unbelievable. However, Einstein's equation, E equals mc, gives us some clues. According to this equation, all the positive energy in stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which shows up as gravity. In a closed universe, or one that will eventually collapse back on itself, these positive and negative energies would perfectly cancel each other out, resulting in a net energy of zero for the universe as a whole. Stephen Hawking wondered how a universe with zero total energy could come from nothing. He suggested that gravity's negative energy could balance out the positive energy needed to create matter. This makes empty space stable. Physicist Alexander Vilenkin expanded on this idea, showing that a small energy-filled vacuum could spontaneously appear from nothing and expand into the universe we see today. This means our universe could have started from a state of nothing where time didn't exist. So, what was there before the Big Bang? The theories we've explored suggest that time itself started with the Big Bang, making the idea of before quite tricky. From singularities to quantum fluctuations, these ideas show just how incredible and mysterious our universe truly is. The Big Bang Theory explains how the universe expanded from an extremely hot and dense state, but it doesn't tell us what happened before that moment. According to the theory, time, space, matter and energy all began with the Big Bang. However, some scientists have ideas about what might have existed before the Big Bang. One interesting idea is the Big Bounce. This theory suggests that the universe goes through cycles of expanding and contracting. Another intriguing idea is the concept of a multiverse. This theory proposes that our universe is just one of many, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another universe entirely. These ideas stretch the boundaries of our current understanding and explore speculative possibilities. They rely on advanced concepts in quantum physics and the still developing field of quantum gravity. Scientists are working to connect the dots between quantum mechanics and general relativity to better understand these possibilities. While these theories offer exciting glimpses into what might have existed before the Big Bang, they remain largely theoretical, highlighting the deep mystery of our universe's origins. By looking back in time, we can explore the origins of each cosmic structure. Each discovery leads to another question: where did this come from, and how did it form? These questions continue until we reach a point where the only honest answer is, we don't know, at least not yet. With what we do understand, we then face the fundamental questions. How did all of this come to be? After the Big Bang, the universe kept expanding and cooling. Initially, it was just a mix of tiny particles. As it cooled, these particles came together to form the first atoms, mainly hydrogen and helium. The life we see today is made possible by complex molecules, which originally evolved from the simple atoms listed in the periodic table. These atoms are the fundamental components of all the ordinary matter in our universe. They weren't just there from the universe's beginning. They formed through countless cycles of stars being born, living and dying. Each cycle of stellar life contributed to the nuclear reactions that produced these atoms, which were then recycled into newer generations of stars. Without this ongoing process, the creation of planets and the complex chemistry needed for life wouldn't have been possible. To understand how the stars and galaxies we see today came to be, a few key factors need to be in place. First, gravity plays a huge role. It pulls together smaller groups of stars and galaxies to form the large galaxies we observe, triggering new rounds of star formation. For gravity to do its job, there must be enough mass already clumped together. This is where dark matter comes in. Early in the universe's history, dark matter formed halos that helped keep the newly formed stars from scattering their material back out into space. Additionally, the right mix of matter, including atoms, dark matter, and radiation, is crucial. This mix not only produced the cosmic microwave background, a kind of afterglow from the Big Bang, but also created the light elements during the hot, dense state of the early universe. The growth of galaxies and star clusters depended on initial small differences in density, often called seed fluctuations, which needed to grow under gravity's influence. Finally, there had to be processes that initially created these density variations, dark matter, and the first batches of ordinary matter. To understand how our universe emerged from the chaos of the Big Bang, we need to consider some critical conditions right from the start. The laws of physics, the fabric of space-time, and the essence of matter energy weren't just there. They had to emerge somehow. We're guaranteed to find an identical copy of our whole universe, as well as countless. Multiple universes now are a genuine possibility, which begs the question: are there other versions of you in a parallel universe? Variations of reality where things are similar to here, but still different, are now considered a genuine possibility. It probably won't surprise you that studying parallel universes was once thought to be completely crazy in the scientific world. It even alienated people who decided to pursue it. But now, theoretical physicists have realized that parallel universes are possible, at least mathematically. One reason for this comes from the strange world of quantum physics. The key thing to remember about quantum mechanics is that it's truly strange. It's the study of subatomic particles, which are the building blocks of everything in the universe. Quantum mechanics tells us that these particles can behave as both particles and waves at the same time. This dual nature splits our reality, creating multiple different universes. The idea is that when you measure a particle that exists in two places at once and find it in one spot, there's another version of you in a different world who finds it in the other spot. Both of these worlds are equally real, so the quantum multiverse isn't separated from us by distance. It's not some far-off place. It's effectively right here in space, but the complexity of quantum dynamics keeps these different branches from interacting with each other. Whether you like it or not, the idea that we live in a multiverse is now the leading scientific view. Another theory is based on mathematical inevitability. If our universe is made from a finite amount of simple matter, then it follows that other universes are made in a very similar way. Just as a house is built from basic building blocks like bricks, everything in our world is made of elementary particles. If a random process arranges these particles in a finite space, there are countless ways this could happen. If this process repeats across an infinite number of other spaces, we're bound to find an identical copy of our universe, as well as countless variations where things are similar but slightly different. There could even be a version of me over there who's identical to me in every way, including feeling that he is me. Another theory, called inflation, explains how the universe expanded rapidly in the first tiny fraction of a second after the Big Bang. This rapid expansion created bubbles or pockets of spacetime where other universes could have formed. If this theory is correct, then these pocket universes might have their own unique laws of physics, meaning there could be another you in those universes who can walk through walls or fly through space. According to quantum theory, a new version of you and a brand new universe is created with every decision you make. For example, every time you flip a coin and say heads or tails, the universe splits into two worlds based on the outcome. Our experience of this is like walking through a garden with paths that fork. When we reach a fork, we choose one path or the other, heads or tails. But both paths exist at the same time, we only experience one of them. There are countless universes out there, with ours being just one. Then there's the patchwork model, which suggests a near-identical copy of our universe exists somewhere else. In this kind of parallel universe, there's another you who is very similar, just with small differences. We're bound to find endless variations where things are like here but still different. For instance, in one universe, the asteroid that wiped out the dinosaurs missed Earth, so there are no humans, just dinosaurs walking around Winchester today. These ideas all suggest that multiple strange and wonderful universes exist out there. While we can't see the entirety of our own universe, scientists think they might be getting closer to understanding these possibilities. Truth often goes through three stages. First, it's ridiculed, then strongly opposed, and finally it becomes self-evident. Perhaps we're now reaching that stage of self-evidence. One mysterious feature within the cosmic microwave background is the cold spot, a large area with lower than average temperatures. An interesting theory about the cold spot is that it might be a cosmic bruise left behind when our universe brushed up against another universe. This idea supports the concept of a multiverse, where multiple universes exist and sometimes interact. In 2007, scientist Laura Massini-Houghton discovered something unusual. She found evidence of our universe colliding with another universe. Scientist Laura Massini-Houghton discovered something unusual. She found evidence that seemed to show two universes crossing over. The detection of a cold spot was one of the signatures she predicted by tracing the quantum entanglement of our universe with other surviving universes. She suggested that this cold spot could have slowed down the expansion in that part of our universe, leading to the cooler temperatures we see today. Recently, there's been a big leap forward in inflation theory, which predicted that if the universe expanded rapidly, it would send ripples through space. These ripples are known as gravitational waves. We hadn't detected anything like this until 2015, when two experiments managed to detect gravitational waves from the merger of two black holes. This detection makes it more likely that we might be able to detect gravitational waves from inflation. But why should we care about whether multiple universes exist? Well, it ties into the age-old question of what our universe is expanding into. If other universes exist, perhaps our universe expands while neighboring ones contract. This could give us more insight into our own universe, especially how it might end. Eventually, our universe could expand until other neighboring universes have their own Big Bang and start expanding into us, causing our universe to contract and possibly end in a big crunch instead of a big bang. Over time, these ideas have led to research about similar anomalies that might look like. According to the theory of cosmic inflation, everything in the universe should be spread out evenly across the sky. But anomalies like the cold spot of the cosmic microwave background challenge this idea, hinting that our universe's history could be more complex than we once thought. British physicist Brian Cox has discussed how the idea of multiple universes fits into a concept called eternal inflation. According to this theory, our universe is just one bubble in a vast space-time filled with other bubbles. These bubble universes are constantly forming. The process begins when a certain region of space stops expanding rapidly. However, not all regions of space stop expanding at the same time. Some areas continue to expand, leading to the ongoing creation of new universes. Each of these universes can have its own unique physical laws, which might be very different from the ones we know. To picture this idea, think of a massive library with countless books. Each book represents a different universe. If the library has an infinite number of books, then every possibility exists in one of them. In one book, gravity could be weaker, allowing creatures to grow taller and buildings to reach much greater heights. In another book, the speed of light might be slower, changing how light and energy behave. But these differences between universes aren't just about physical laws. They could include completely different histories and evolutions. Imagine a universe where dinosaurs never went extinct and became the dominant intelligent species. Or think of a universe where the basic elements of matter are different, leading to planets and stars made from dark matter instead of the substances we're familiar with. When we look up at the night sky, we see stars, planets, and galaxies scattered across the vastness of space. Yet, everything we can see with our eyes, telescopes, and other instruments accounts for only a small fraction of the entire universe. The estimation of the universe we can observe is believed to be only 5%. The other 95% is something we can't directly observe. This 95% is something we haven't been able to discover. This hidden majority is made up of dark matter and dark energy, two mysterious components that play a crucial role in the structure of the universe. But why can't we see this 95%? And what does it mean for our understanding of the cosmos? To understand what we can't see, let's first talk about what we can see. The observable universe includes all the matter that emits, reflects, or interacts with light or other forms of electromagnetic radiation. This includes stars, planets, galaxies, nebulae, and even the cosmic microwave background radiation, which is the afterglow of the Big Bang. When astronomers use telescopes to observe the universe, they rely on light to gather information. For example, when you look at the night sky, you're seeing light that has traveled across space for years, even millions of years, before reaching your eyes. This light carries information about the objects it came from, allowing scientists to study their composition, distance, motion, and much more. However, this visible matter that makes up stars, planets, and galaxies represents only a tiny portion of the universe's total content. The other 95% of the universe is composed of two undetected components: dark matter and dark energy. Dark matter makes up about 25 to 27% of the universe. We can only detect it through its gravitational effects on visible matter. Dark matter acts like a cosmic framework, guiding the structure and formation of galaxies. The most hardest to understand component is dark energy, which makes up roughly 68% of the universe. This mysterious force causes the universe to expand faster and faster. Together, these components make up the fabric of the cosmos, influencing everything from the smallest particles to the largest galactic structures. We don't yet know exactly what dark matter and dark energy are, but we're fairly certain they exist. So, what do we know? Unlike the matter we're familiar with, dark matter doesn't emit, absorb, or reflect light, which makes it completely invisible to us. We can't see it with telescopes, and we can't detect it using any of our traditional methods. So how do we know it exists? The existence of dark matter was first proposed when astronomers observed that galaxies were rotating much faster than they should be, based on the amount of visible matter they contain. According to the laws of physics, if a galaxy contains only the matter we can see, its outer edges should rotate more slowly than its inner regions. However, observations show that the outer parts of galaxies were moving just as fast as the inner parts, suggesting that something else invisible was providing extra gravitational pull. This invisible substance is what we now call dark matter. Although we can't see dark matter directly, we can observe its effects on visible matter. For example, when light from distant galaxies passes through a region of space with a lot of dark matter, the light bends, a phenomenon known as gravitational lensing. This bending effect allows astronomers to map the distribution of dark matter in the universe, even though they can't see it directly. But what is dark matter made of? This is one of the biggest unanswered questions in modern physics. Some theories suggest that dark matter could be made of particles that don't interact with light or other electromagnetic forces, which is why they remain invisible. These particles might only interact through gravity, which is why we can detect dark matter's gravitational effects, but not the matter itself. Even more mysterious than dark matter is dark energy, which makes up about 68% of the universe. Dark energy is believed to be responsible for the accelerating expansion of the universe. For most of the 20th century, scientists thought that the expansion of the universe, which began with the Big Bang, would gradually slow down over time due to the gravitational pull of all the matter in the universe. However, when astronomers observed distant supernovae, they found that these objects were farther away than expected, indicating that the expansion of the universe was actually speeding up. This unexpected acceleration led to the idea that some unknown force, now called dark energy, is driving the expansion. But what is dark energy? Like dark matter, we don't know exactly what it is. Some theories suggest that dark energy could be a property of space itself, while others propose that it could be related to a new unknown field or particle. Scientists are pretty sure they exist. Why? Because dark matter is essential for galaxies to form in the first place. When scientists studied the structure of the universe, they realized that the amount of visible matter isn't enough to explain how galaxies hold together. The gravity from visible matter alone isn't strong enough to form galaxies or complex systems. Without dark matter, stars would likely be scattered randomly instead of gathering into the galaxies we see. This suggests that dark matter acts like glue, holding everything together. Even though dark matter is invisible, it can be detected indirectly. In areas with a lot of dark matter, light passing nearby gets bent, creating a lensing effect. This bending of light reveals where dark matter is based on its gravitational pull. So, what isn't dark matter? First, it's not just ordinary matter without stars. Regular matter gives off detectable particles, making it visible. If dark matter were just ordinary matter, we would have already seen it. It's also not antimatter. When antimatter meets regular matter, it emits gamma rays. If dark matter were antimatter, we would detect these rays, but we haven't. Dark matter isn't made of black holes either. Black holes are dense objects with a strong influence on their surroundings, while dark matter seems to be spread out across space. The gravitational effects of black holes are different from what we observe with dark matter. Scientists are still testing different ideas and running experiments to figure out what dark matter really is. Even with precise tools like the European Space Agency's Planck spacecraft, we can only detect less than 5% of the total observable universe. For years, scientists have been trying to solve the mystery of dark matter, but so far we only know it's there because of its gravitational effects on visible matter. British physicist Brian Cox suggests that dark matter could be made up of particles we haven't discovered yet. But how do we actually find dark matter? Scientists are on the hunt for this mysterious substance using the world's biggest physics experiment at the Large Hadron Collider, Switzerland. Instead of just trying to detect dark matter, they're attempting to create it from scratch. They do this by smashing known particles together at extremely high speeds, creating massive amounts of energy. This energy might produce particles of dark matter. When protons collide, they usually create new particles, but most of them are lightweight. Occasionally, these collisions create much heavier particles, and those are the ones scientists are hoping to find. Scientists believe they're getting closer to figuring out what it's made of. One of the main candidates for dark matter is the weakly interacting massive particles. These particles are thought to interact very weakly with normal matter, making them incredibly hard to detect. Underground detectors are designed to catch these rare interactions and provide clues about dark matter. One interesting piece of evidence comes from gravitational lensing. This happens when light from faraway objects, like galaxies or quasars, gets bent around a massive object, like a galaxy cluster, because of gravity. The amount of bending shows us that dark matter is there, adding to the overall gravitational pull. Astronomers also play a big role in the search for dark matter. By studying the night sky, they look at how galaxies and galaxy clusters move. The way these large structures behave suggests there's more mass present than we can see, and that's where dark matter comes in. For example, when astronomers observe how fast stars orbit around the center of galaxies, they notice that there must be extra invisible mass, likely dark matter, holding everything together. Even though we haven't directly found dark matter yet, every experiment brings us closer to understanding this mysterious part of the universe. dark energy is even more mysterious than dark matter. It's a type of energy that we can't directly detect or measure, but we can see its effects. Unlike dark matter, which clumps together due to gravity, dark energy is spread evenly across space. In 1929, astronomer Edwin Hubble made a groundbreaking discovery. He noticed that light from distant galaxies shifts towards the red end of the spectrum as it travels through space. This effect, known as redshift, revealed something surprising. Hubble found that the farther away a galaxy is, the more its light is redshifted, while closer galaxies show less redshift. He figured out that this happens because the universe is expanding. As light stretches out, it shifts towards the red part of the spectrum, showing that space itself is getting bigger. Recent discoveries have taken Hubble's findings even further. The universe isn't just expanding, it's speeding up. Scientists used to think that gravity would eventually slow down this expansion or even reverse it. But now they know that dark energy is driving this rapid expansion, pushing the universe apart faster and faster. Space itself doesn't change as it expands. Instead, new space is constantly being created everywhere. Galaxies stay held together by gravity, so we don't feel this expansion in our daily lives. But we can see it happening all over the universe. Wherever there's empty space, more is being created every second. So, what exactly is dark energy? It seems to be a type of energy in empty space that's stronger than anything else we know and keeps growing. Empty space contains more energy than everything else in the universe combined. This mysterious force is pushing galaxies apart and making the universe expand even faster. Dark energy remains one of the biggest mysteries in cosmology. While we can't directly detect or measure it, its impact on the universe is clear. For now, we certainly know the reason why we can't see 95% of the universe is that dark matter and dark energy don't interact with light or other forms of electromagnetic radiation in the same way that ordinary matter does. Instead, we conclude their existence based on their effects on the visible universe. For dark matter, this includes its gravitational influence on galaxies and the bending of light. For dark energy, it's the observation that the universe's expansion is accelerating rather than slowing down. In a sense, the visible universe is just the tip of the iceberg. The stars, planets, and galaxies we can see are like the visible peaks above the waterline, while the vast majority of the universe lies hidden beneath the surface, unseen and mysterious. Take a close look at this picture. This is Eugene Cernan, the last astronaut from the Apollo program to walk on the moon. But something seems off. Do you notice it? The night sky looks completely empty with no stars at all. In fact, every photo taken during the Apollo missions shows a sky empty of stars. Even though the universe is filled with trillions of stars, the Apollo astronauts said they couldn't see a single star from the moon. This lack of stars has fueled conspiracy theories, with some people claiming that the moon landing was fake. But the real explanation is much more interesting and goes deeper than any conspiracy theory. The reason stars don't appear in photos taken on the moon is primarily due to the camera settings. When astronauts take pictures on the moon, they usually capture the brightly lit lunar surface. The moon's surface is illuminated by the sun, and to capture this brightness correctly, the camera uses a fast shutter speed and a low ISO setting. But still, when we see the night sky from Earth, we see mostly darkness. Why does space look empty? This problem was first raised by the German astronomer Johannes Kepler in 1610. Our galaxy, the Milky Way, is huge, with an estimated 100 to 400 billion stars. On top of that, The observable universe has trillions of galaxies, each with trillions of stars. Careful study suggests that the sky should be as bright as the surface of the sun. Yet, when we look up at night, we mostly see darkness. This puzzle, known as Olbers' paradox, took nearly 300 years to solve. With so many stars in every direction, astronomers wondered why the entire sky isn't bright and full of light. Olbers' paradox is based on the steady-state theory. Imagine a universe where everything has always stayed the same and always will. The position of stars, galaxies, everything. This was the main idea behind the steady-state theory, which used to be the most popular explanation of the universe. It said the universe was infinite, without a beginning or end, uniform in every direction, and not expanding. With this theory in mind, astronomers faced a big question. If the universe is full of stars and has always existed, why is the night sky dark? According to the steady-state theory, even the light from the farthest stars should have reached us by now, filling the sky with their glow. One early idea was that maybe the stars are just too far away to affect our night sky. But this didn't make sense with the steady-state model. If the universe is infinitely old, there's been plenty of time for the light from any star to reach Earth, even from the farthest parts of the universe. This light should fill the sky, leaving no dark areas. Johannes Kepler had a different idea to solve the paradox, which went against the steady-state theory. He suggested that the universe isn't infinite. Instead, he thought the stars only spread out to a certain limit, and beyond that, there was just empty space. This idea was interesting, but it raised new questions. How far does this space with stars go, and what's beyond that edge? Kepler's idea of a limited universe had its own issues. If the universe had a boundary, the combined gravity of all the stars and planets could pull everything back together, causing the universe to collapse. Because of these challenges, most astronomers kept believing the universe was infinite. This meant the paradox and the steady-state theory remained unsolved for nearly 200 years. Then, a famous German astronomer named Heinrich Olbers brought attention back to this old question. Why is the night sky dark and looks empty? Since then, Olbers' name has become closely tied to the paradox. At the time, people still believed the universe was unchanging. Olbers suggested a simple idea. If the universe is infinite, it would be full of dust and rocks. These particles could block the light from distant stars, making them look dimmer to us. This cosmic dust and rocks would absorb and block starlight as they move through space. Today, many people still think about space like Olbers did, similar to how clouds block sunlight and hide the sky. Just like clouds, cosmic dust and rocks can obscure the light from stars. But Olbers' explanation wasn't the whole story. Over time, the dust and rocks blocking the light would heat up and start glowing themselves. This means the universe would still be filled with light, just like before. The dust and rocks would only temporarily block the starlight before releasing it again. So, the total amount of light reaching us would stay the same. So, what actually solves this mystery? It took another 100 years to find the real answer. In 1929, Edwin Hubble used his powerful telescope, hoping to find evidence that the universe was shrinking, which would support the idea of a limited universe like Kepler suggested. But instead, Hubble found that galaxies were moving away from us, and the farther a galaxy was, the faster it seemed to be moving away. This showed that the universe wasn't staying the same or collapsing, it was actually expanding. This discovery led to a new question. What does an expanding universe mean for its beginning? Scientists now believe the universe started as something incredibly tiny and dense. It then expanded rapidly in a process called cosmic inflation. As it expanded, it cooled down, and eventually stars and galaxies began to form. This understanding led to what we now call the Big Bang Theory. Scientists think this all started about 13.8 billion years ago, and it's currently our best explanation for how the universe began. Today, most scientists agree that the universe is around 13.8 billion years old. When we look at light that's 13.8 billion years old, we don't see stars not because the light hasn't reached us, but because we're looking back to a time before stars even existed. The farther we look into space, the farther back in time we're seeing, until we reach what seems like the edge of the universe. This isn't a real edge, but rather the oldest light we can see, known as the cosmic microwave background. It's the leftover glow from the Big Bang. When we use telescopes to look beyond the earliest stars, we see this special type of light. This isn't light from stars, but light left over from the Big Bang. It forms a background glow beyond where the stars are. However, the Big Bang Theory brings up a new issue. It suggests that the universe used to be much brighter, especially during a time called the recombination era. Back then, the whole sky would have been as bright as the sun because the universe was very hot. This means that the background glow from the Big Bang, known as cosmic background radiation, should be very bright. According to Olbers' paradox, this bright background should make it hard for us to see any faint stars in the night sky. Since the Big Bang happened 13.8 billion years ago, the universe has followed three main rules as it grows and changes. First, at the beginning, the universe was incredibly tiny, very dense, and extremely hot. Second, just a fraction of a second after it started, the universe began to expand and cool down. Third, and this is really important, the universe will keep expanding and cooling. Astronomers believe this will continue until the universe becomes so cold that all heat disappears, a scenario they call the heat death of the universe, also known as the Big Freeze. In this future scenario, the universe will have expanded so much that it cools down completely, and all heat energy will be gone. These rules show us that our universe has been getting bigger for the last 13.8 billion years. When the universe started, it was filled with very bright and hot light. As the universe expanded, this light stretched out, turning into longer wavelengths, making it cooler and dimmer. This stretching of light is known as the redshift effect. It's why the cosmic background radiation isn't extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expanding universe solve Olbers' paradox. The universe started from a single point and quickly expanded during the Big Bang. Over billions of years, it has cooled down. Because the universe isn't infinitely old, there's a limit to how far we can see into space. The redshift effect also makes the light from distant objects appear dimmer. These factors together explain why the night sky looks dark today. The darkness of the night sky shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe started with the Big Bang and has been expanding ever since. The night sky is a quiet reminder of how the universe began as a very hot and dense place. This understanding not only solves Olbers' paradox, but also helps us appreciate how amazing and complex the universe really is. With 8 planets and numerous celestial objects, our own solar system is one of the countless planetary systems scattered across the Milky Galaxy. In addition, there are over 1 million smaller objects like asteroids, comets, and meteoroids. The planet farthest from the Sun that we know of is Neptune, which orbits about 30 astronomical units away, roughly 4 light hours. But Neptune's orbit covers only a tiny part of our solar system. The most distant object discovered in our solar system so far is called Far, Far Out, which is 132 astronomical units, or 18 light hours, away from the Sun. Even so, this object is still nowhere near the edge of the Oort cloud, which starts about 2,000 astronomical units from the Sun. The Oort cloud's outer boundary might stretch as far as 60,000 astronomical units, or about 1 light-year. These limits are set by the Sun's gravitational pull, and beyond that lies interstellar space. As we move further out, we find over 50 stars within 20 light-years of the Sun. These stars vary widely, from dim, cold brown dwarfs to bright, well-known stars like Sirius, Procyon, and Altair. Some of these stars have their own planetary systems, and some of those planets might be capable of supporting life. For example, Gliese 832c, located 16.1 light-years from the Sun, is more similar to Earth than any other planet in our solar system. The average temperature on Gliese 832s is around 153 Kelvin, or about 20 degrees Celsius below zero, and it takes only 36 Earth days to complete an orbit around its star. In astronomical terms, the distance between us and Gliese 832s is relatively small. However, if a space probe were to leave our solar system, traveling at about 17 kilometers per second, it would still take around 300,000 years to reach Gliese 832c. With our current technology, it's impossible to design a spaceship that could make such a long journey. Our solar system, along with nearby stars, is part of the Orion Arm, which is itself a part of the Milky Way. The Milky Way is estimated to contain about 400 billion stars and potentially over 1 trillion exoplanets. Today, we estimate that the Milky Way is around 100,000 light-years across, with its outer halo possibly being twice that size. The main disk of the Milky Way is about 1,000 light-years thick, and there's a central bulge that's about 3,000 light-years thick. The Milky Way is part of a group of over 50 galaxies called the Local Group. This group of galaxies spans an area of space about 10 million light-years across. The largest galaxies in the Local Group are the Andromeda Galaxy, the Triangulum Galaxy, and the Milky Way. The total mass of the Local Group could be as much as 3 trillion times the mass of the Sun, with the Milky Way and Andromeda making up most of that mass. Andromeda, which is about 2.5 million light-years from Earth, is the closest large galaxy to us, apart from smaller or dwarf galaxies. Going even further, the Local Group is part of the Virgo supercluster, a massive structure containing over 30,000 galaxies. This supercluster stretches across a space about 150 million light-years wide and has a total mass equal to about 1,000 Milky Ways. The Virgo supercluster is somewhat flattened, with about 60% of its galaxies forming a flat sheet that's around 10 million light-years thick. While this may seem huge, it's actually small when compared to the larger structure of the universe. If we zoom out even more, we can see a giant supercluster of galaxies called Laniakea, which is about 520 million light-years across. Laniakea includes several superclusters of galaxies, including the Virgo supercluster and an area known as the Great Attractor. The total mass of Laniakea is roughly 100 quadrillion times the mass of the Sun. The Great Attractor, located about 250 million light-years away, is the gravitational center for nearby objects. However, it can't be directly observed from Earth because the Milky Way blocks our view, which is why the nature of the Great Attractor is still a mystery. Laniakea is part of the large-scale structure of the universe, a complex system of galactic filaments, walls, and vast voids in huge empty spaces in the cosmos. Some of these structures are incredibly massive. For example, the Hercules Corona Borealis Great Wall stretches for an astounding 10 billion light-years. Since its discovery in 2013, this superstructure has been considered the largest known feature in the universe. It likely contains millions of galaxies with an uncountable number of stars. The existence of such a colossal structure is a mystery to scientists, as our current understanding of the universe's evolution suggests that something so large shouldn't be able to form. Yet, despite its enormous size, this wall is still just a tiny part of the observable universe. According to current cosmological theories, space and the universe are constantly expanding, with the rate of expansion depending on the distance between objects. The further away an object is, the faster the distance between it and the observer increases. This expansion isn't limited by the speed of light because it's space itself that is stretching. As a result, at a certain distance, two objects will become unobservable from each other. Observations of the cosmic microwave backgrounds suggest that the observable universe is a sphere with a diameter of roughly 93 billion light-years. According to the theory of relativity, we can only see and interact with objects within this sphere. This spherical area in space is called the metagalaxy, and it might represent the entire universe or just a small part of it. Hypothetically, there could be unknown structures beyond the visible boundaries of space. These are referred to as extra-metagalactic objects, but unfortunately, we can't study them with current scientific methods. However, some astronomical bodies at the edge of the visible universe seem to move in ways that don't match our expectations based on the data we have. These unusual movements might suggest the presence of massive structures beyond the boundaries of the metagalaxy, whose gravitational pull affects nearby objects. There are many hypotheses about what lies beyond the metagalaxy, but most are more philosophical than scientific. For example, some believe that time and space as we know them don't exist beyond the boundaries of the universe. The physical laws we're familiar with might not apply there, and concepts like matter and energy could be meaningless. This idea suggests that the metagalaxy is just a part of an even more complex and larger structure in space, with dimensions and properties beyond our understanding. It's possible that this structure exists in a multi-dimensional space or operates on physical principles we have yet to discover, making the metagalaxy just a small piece of something far more incredible. According to some interpretations of the Anthropic Principle, there might be other worlds beyond the boundaries of the observable universe. In these worlds, the fundamental constants, like the speed of light or the charge of an electron, could be completely different. This idea is supported by the concept of a multiverse, which can be imagined as a foam with many bubbles, each separated by thin walls. These walls are impenetrable, meaning that every universe is its own separate space with its own physical laws. These laws might be totally different from the ones we know. The most radical ideas even suggest that our world might not have any objective reality at all. According to these theories, the universe could be a simulation, like an incredibly advanced form of virtual reality. These ideas usually propose that some superbeings or supercivilizations exist beyond the reality we're familiar with, beings whose level of advancement is far beyond ours and whose goals and abilities are impossible for us to understand. Of course, it's nearly impossible to either prove or disprove these theories. The distances in space are so vast that they're almost impossible to imagine and can even seem frightening. They appear infinite from our perspective today. What we do know is that the universe is expanding, and if this continues, there will come a point where space objects will disappear one after another beyond the event horizon. First galaxies, then stars and the universe will eventually be plunged into eternal darkness. But by that time, there may be no one left to witness it. Our yellow dwarf star-sun, which provides us with light and warmth every day, is located on the outskirts of the Milky Way galaxy. It orbits around the galaxy's center, following a path known as the co-rotation circle. This means the Sun's movement is synchronized with the rotation of the galaxy's spiral arms, where new stars are born. Thanks to this alignment, the solar system rarely crosses into these arms, keeping us safe from harmful supernova explosions and the intense heat of active stars. The distance of the Sun's orbit from the center of the Milky Way is also important. If the Sun were closer to the center, the abundance of heavy elements would have made forming planets too large and massive. Moreover, the intense radiation from the galactic core would have made it nearly impossible for life to develop on these planets. On the other hand, if the Sun were farther from the center, the lack of diverse elements would mean that rocky planets like Earth, rich in various chemicals, wouldn't have formed. Instead, the Sun would likely be surrounded by only gas giants or icy worlds. There are also interesting coincidences within our solar system. For example, Earth is positioned at just the right distance from the Sun and follows a stable, nearly circular orbit. If Earth's orbit were just 5% closer or farther from the Sun, our planet would either be frozen over or covered in a thick layer of water vapor. In either case, advanced life as we know it wouldn't exist. The Sun itself has several critical characteristics. It's not too hot, not too cold, and has a long lifespan. Although hotter stars create wide habitable zones, they don't last long enough, and their radiation is too intense. Cooler stars, like red dwarfs, have narrow habitable zones, often too close to the star, which can cause planets to become tidally locked. This means one side of the planet is always facing the star, leading to extreme temperature differences between the two sides. Some might argue that life adapted to the conditions on Earth rather than Earth being perfectly suited for life. While this is a reasonable point, there are deeper aspects of the universe that challenge this idea. For instance, stable orbits for celestial bodies are only possible in a three-dimensional space. In other dimensions, the orbits of electrons within atoms would become unstable, causing atoms to either collapse or fly apart. This means atoms, and by extension matter, couldn't exist in a universe with more than 3 dimensions. It would only contain radiation and free particles. Another important point is the existence of fundamental constants that all of modern physics relies on, like the speed of light, the gravitational constant, Planck's constant, and the masses of the electron and proton. These values have been determined through experiments, and while they are considered independent of each other, science has yet to explain why they have the specific values they do. For example, the mass of a proton is slightly more than that of an electron, and this small difference is crucial. Without it, the proton-electron system wouldn't exist. Hydrogen atoms would turn into neutrons, and there would be no hydrogen in the universe. Without hydrogen, stars wouldn't form, and heavier elements wouldn't exist either. If the values of the strong nuclear force were even slightly different from what they are today, the nuclear reactions that power stars wouldn't be possible. If the gravitational constant were stronger, stars would compress too much, leading to the formation of many large hot stars with very short lifespans. After they burn out, most of the matter in the universe would end up trapped in black holes and neutron stars, leaving little material to form planets, moons, and other space objects. On the other hand, if the gravitational constant were weaker, interstellar gas wouldn't compress enough for nuclear reactions to become self-sustaining. In that case, stars wouldn't ignite, and the universe would be filled with giant brown dwarfs instead. Any change in the electromagnetic force would make chemical reactions and the formation of complex compounds nearly impossible. If the Coulomb force were stronger, no elements heavier than boron would exist because their nuclei would be torn apart by the repulsion between protons. The formation of heavy elements in the universe relies on several factors working together perfectly. For example, a special state of carbon, known as carbon resonance, allows helium to fuse into carbon. This process is crucial for the creation of heavy elements and their distribution throughout the universe. Carbon resonance is also the reason why stars go supernova, shedding their outer layers. The atoms created inside these stars are spread across space, eventually forming planets, moons, asteroids, and other celestial bodies. Moreover, carbon is essential for life because it can form long and complex chains, which are the basis for a vast array of chemical compounds. Life, as we know it, relies on organic compounds that wouldn't exist without carbon. So, it becomes clear that the universe, life within it, and intelligent beings like us exist because of a series of remarkable and not so obvious coincidences. Theories that explain this often go beyond physics and delve into philosophy. One such theory is the Anthropic Principle. Although the term was coined in 1973, the ideas behind it were expressed much earlier. For example, Soviet scientist Grigory Idlis wrote in 1958 that what we observe in the universe is not random. It is a part that has been made suitable for the development of life due to its special structure. This perspective is known as the weak anthropic principle. Later on, the strong anthropic principle was introduced, which suggests that the universe must have certain properties that allow intelligent life to evolve. In other words, an observer is necessary for the universe to exist. This idea is related to quantum physics, where the presence of an observer significantly affects the behavior of particles. That's why an observer is essential in any quantum experiment. The laws of the universe are what they are because we can only exist in a universe with these specific laws. The Anthropic Principle suggests that there might be other universes or different parts of our own universe that follow different physical laws. However, either we are unable to observe these places, or those hypothetical worlds can't exist without someone to observe them. This idea can lead to theories like the multiverse, where the basic physical constants could change over time. Yet, all observations in the parts of the universe we can see show that these fundamental values remain consistent. The concept of a multiverse is difficult to describe within the limits of science. In general, the Anthropic Principle goes beyond the scientific view of the world and leans more toward metaphysical thinking. As Stanislav Lem once said, it's an attempt to explain the unknown with the unknown. The Anthropic Principle also seems to conflict with the mediocrity principle. The mediocrity principle states that the part of space we can observe isn't anything special, and that there are many similar regions in the universe. For instance, the Milky Way doesn't have any particularly unique features, and its position in the universe isn't remarkable compared to billions of other galaxies. Additionally, there's the principle of space homogeneity, widely accepted in modern physics, which means that natural laws are the same everywhere in space. This idea is supported by countless observations of the universe around us. Humans have always been curious about these big questions. Are we alone in the universe? Is Earth unique? Are there other Earth-like planets in the Milky Way? Science hasn't been able to provide clear answers to these questions yet. If it could, it would likely lead to a complete revolution in our understanding of the world, taking our knowledge to a whole new level. Until then, everyone is free to form their own opinions. When we think about how huge the universe is, it's obvious to wonder if we really matter. Are we special, or are there other life forms out there in the cosmos? This brings up the question, was the universe made specifically with us in mind? This idea is linked to the Anthropic Principle that we have discussed. It suggests that the universe's basic laws and constants seem perfectly set up to support life, especially intelligent life like humans. For example, the exact strength of gravity, electromagnetic forces, and how atoms work are all crucial for life. Even small changes in these constants could make life as we know it impossible. So, does the fact that the universe is so precisely tuned mean it was designed just for us? Some people think the conditions that allow life are too perfect to be a coincidence, suggesting there might be a purpose behind it. On the other hand, others believe that this fine-tuning is just the result of natural processes and random chance. They argue that in a universe as vast as ours, it's not surprising that at least one planet, like Earth, ended up with the right conditions for life. The multiverse theory adds another perspective. It suggests that our universe might be just one of many, each with its own set of physical laws and constants. In this multiverse, only a few universes might have the right conditions for life. If this theory is true, our universe isn't particularly unique. It's just one of the few where life could happen, making the idea of fine-tuning less remarkable. The search for life beyond Earth also affects this discussion. Finding life elsewhere, whether it's microbes on Mars, in the oceans of moons like Europa and Enceladus, or on distant exoplanets, would suggest that life isn't unique to Earth, but could exist wherever the conditions are right. Such discoveries could change how we think about the rarity of life in the universe. Beyond science, philosophical views also influence how we understand the universe. Some people find comfort in believing that the universe has a specific purpose, while others see beauty in its randomness and endless possibilities. Whether or not the universe has an intent, our natural curiosity and desire to explore are key human traits. Asking these big questions not only drives scientific progress, but also helps us better understand the cosmos. Science shows us a universe that is vast and seemingly indifferent, which can make us feel small. Yet, some argue that we might still have a special place in the cosmos because the laws of physics are so perfectly tuned to make life possible. For instance, the exact strength of the electromagnetic force is crucial for stars to produce carbon, which is essential for life. Even the energy in empty space seems to be set just right for intelligent life to emerge. This idea of fine-tuning has led to different interpretations of the Anthropic Principle. One view suggests that the universe was purposefully designed with us in mind, possibly by a higher intelligence. Another idea, known as the life principle, proposes that life is a natural part of the universe's makeup. However, these ideas are not widely accepted in the scientific community. Another way to look at the Anthropic Principle is to say that the universe exists because we are here to observe it. A more practical view is that the universe seems perfectly suited for us simply because we live in a part of it that supports life. This could be due to the possibility of multiple universes, each with its own set of physical laws, with ours being one of the few that can support life. The famous American writer Ursula Le Guin once wrote, "The word must be heard in silence. There must be darkness to see the stars." This thought reflects the idea that everything in the universe has a beginning and an end. Some subatomic particles exist for just fractions of a second. Some microorganisms live for a few hours or days, and humans live for several decades. Even stars eventually burn out after millions or billions of years. But what about the universe itself? Will it also come to an end? What will that look like? And what happens after the universe dies? The earliest theory about the universe's origin is called the steady-state theory. Supporters of this theory believed that the universe has no beginning or end. It has always existed and always will in a state of equilibrium. However, scientific discoveries eventually show that this theory is likely wrong because there are irreversible processes happening in the universe. In the 1910s and 1920s, the Big Bang theory was developed and became widely accepted. Today, it is one of the most consistent scientific explanations for the origin and evolution of the universe. Many scientists contributed to the development of the Big Bang theory, with Albert Einstein's work on the general theory of relativity providing the foundation. The main idea of this theory is that the fate of the universe depends on dark energy, a mysterious force that causes space to expand. However, we still don't fully understand dark energy, and there are many theories about it, each with its strengths and weaknesses. According to current estimates, the universe is about 14 billion years old, based on the time since the Big Bang. The universe is constantly expanding, and depending on the behavior of dark energy, it will either continue expanding forever at an increasing rate, or the expansion will slow down and eventually reverse. In the latter case, the universe could collapse back into an infinitely small point, similar to how it began. Science doesn't yet know which of these possibilities will happen, but it offers two possible scenarios: the Big Rip and the Big Crunch. The rate at which the universe expands is related to the distance between objects. The farther apart they are, the faster they move away from each other. Imagine a balloon being inflated with air. If you put two dots on the balloon and then inflate it, the dots move farther apart. That's how the expansion of the universe works. It's space itself that's expanding. The farther apart the dots are, the faster they move away from each other. At a certain point, this expansion rate becomes faster than the speed of light. This point is known as the event horizon. Objects beyond this horizon disappear from view, moving beyond the reach of even the most advanced telescopes, never to be seen again. First, the most distant galaxies and clusters will disappear from the sky. Then, one by one, the stars of the Milky Way will fade away. Eventually, our own sun will dim and vanish. It's a bleak vision of the future. If the Big Rip theory turns out to be correct, the universe's expansion will keep accelerating. This will eventually cause the forces of expansion to overcome the pull of gravity. First, galaxy clusters would start to break apart, followed by the galaxies themselves, and then star clusters. After that, even stellar systems would disintegrate, as stars would no longer be able to hold onto their planets and moons. Eventually, matter would break down into atoms, and those atoms would break down into subatomic particles. At that point, matter as we know it would cease to exist. Beyond this, the physical laws we understand would no longer apply, and what happens next is impossible to predict. Current observations show that space is expanding, and the rate of this expansion is increasing. However, we don't fully understand the nature of dark energy. It could have properties we're not aware of, which might reverse the expansion. If that happens, the universe could start to contract. This could occur if the overall gravitational pull from all the matter in the universe becomes stronger than the expansion force. This scenario is known as the Big Crunch. In this case, the universe would continue to shrink until it's about 5 times smaller than it is now. Galaxy clusters would merge into one massive supercluster, filling the much smaller universe. Meanwhile, inside galaxies, events like star formation, star deaths, and planet formation would continue just as they do now. As the universe continues to contract, its volume will eventually shrink to just 1% of what it is today, and all the galaxies will merge into one. By then, the temperature of the leftover radiation will have risen to 274 degrees Kelvin and will keep increasing. This rise in temperature means there won't be any liquid water left in the universe, which is essential for life as we know it. As the universe continues to contract and heat up, planets will first burn and then melt, and all matter will collapse into a massive cloud of boiling plasma. Eventually, even atoms and subatomic particles will break apart, and the universe will collapse into a singularity, similar to how it was at its beginning. There's another theory related to the Big Crunch, known as the Big Bounce theory. According to this idea, after the universe collapses into a singularity following the Big Crunch, It could be reborn in a new Big Bang, starting the cycle over again. This process could repeat itself endlessly, as far as we can talk about eternity in a situation where time and space no longer exist. Our understanding of dark energy is still too limited to say for sure how long any of these scenarios might take. For all we know, the next big rip or big crunch could happen while stars and planets still exist. But what if that isn't the case? What will happen to the universe if its ultimate end is still far off in the future? The laws of physics suggest that the universe, as we know it, cannot last forever. Cosmology identifies 4 main epochs, each associated with a specific phase of the universe. We are currently in the stelliferous era. During this time, there's plenty of interstellar gas, which serves as the raw material for star formation. New stars continue to form from this gas, but this process will eventually stop when all the interstellar gas is used up. This era is expected to end sometime between 1 and 100 trillion years from now. By then, the Sun and most other stars will have burned through their nuclear fuel, turning into white dwarfs, neutron stars, or black holes. We live in a world with 3 dimensions: up and down, left and right, and forward and backward. These are the directions we can move in. Time is another dimension we experience, moving from the past to the future. Together, these make up what we call spacitime. In physics, dimensions are like different directions you can move in, similar to lines on a graph. Normally, we only notice 3 dimensions. But what if there are more dimensions that we can't see? Theories like string theory and M theory suggest there might be extra dimensions. According to string theory, the smallest parts of our universe aren't tiny points but small, vibrating loops of energy called strings. The maths behind string theory suggests that there need to be 10 or 11 dimensions for everything to work correctly. String theory tries to explain all the natural forces like gravity, electromagnetism, and the forces inside atoms by saying everything is made of these strings. The way these strings vibrate determines the type of particles they become. So why can't we see these extra dimensions? They might be incredibly small and tightly folded up, making them impossible to detect with our current tools. For example, imagine an ant walking on a tightrope. To the ant, the rope looks like a line because it can't see its width. Similarly, these extra dimensions could exist but be too small or hidden for us to notice. If these higher dimensions are real, they could help us solve some big questions in physics, like why gravity is much weaker than other forces. Maybe gravity spreads out into these extra dimensions, making it seem weaker in our 3-dimensional world. These higher dimensions could help us better understand particles and forces. They could connect all the different forces into one complete picture, leading to new technologies and a deeper understanding of the universe. Scientists are looking for evidence of these higher dimensions. One way is by studying how gravity behaves at very tiny scales. If higher dimensions are real, they could cause slight differences in gravity, which we might notice in lab experiments. Another method involves high-energy particle collisions, like those at the Large Hadron Collider. In these experiments, particles are smashed together at high speeds. If any particles disappear into higher dimensions, it could be a clue that these dimensions exist. There are also other interesting ideas about higher dimensions. For example, some theories suggest that our universe might be a 3-dimensional brain floating in a space with more dimensions. In this idea of a brain world, our universe could be just one of many parallel universes, each existing as a separate brain in a space with extra dimensions. This raises exciting possibilities about how these universes might interact, like through gravity or by exchanging particles. Another idea related to higher dimensions is the multiverse theory. This theory suggests that our universe is just one bubble in a vast space filled with other universes, each existing in a higher dimension. These different universes could have their own physical rules and might even interact with each other. For example, if these universes were to collide, it could create a massive explosion similar to the Big Bang that started our universe. While the idea of higher dimensions is fascinating, it remains a theory. One of the biggest challenges is that these dimensions are not something we can currently see or measure directly. To detect them, we would need extremely high energy or very precise measurements, which are beyond what we can do with today's technology. Mathematics plays a key role in helping us explore the concept of higher dimensions. Many of the theories suggesting the existence of these extra dimensions rely on complex maths from areas like geometry, topology, and algebra. These branches of maths help us imagine and understand spaces that go beyond the three dimensions we usually think about. Mathematicians and physicists work together to create models that predict how these higher dimensions might affect what we can observe in the universe. They then test these models with experiments and observations. Quantum mechanics, which studies how particles behave at very small scales, could also be influenced by higher dimensions. The strange and often puzzling behaviors we see in quantum mechanics might be due to interactions happening in spaces with more than three dimensions. So, do higher dimensions really exist in the universe? While we don't have concrete proof yet, the possibility of higher dimensions is an exciting area of research in theoretical physics. If these dimensions are real, they could change how we see the universe and reveal new insights about the nature of reality. The Earth is spinning faster. Could this lead to tech problems? And what do melting glaciers have to do with it? You might know there are 86,160 seconds in a day. But in 2021, scientists found that the average day is 0.05 milliseconds shorter than that. This means the Earth is spinning faster than usual. You might think 0.05 milliseconds, what's the big deal? But this is surprising because it goes against what we normally expect. Since it formed, the Earth's spin has been slowing down. In the distant past, days on Earth were much shorter. But what does a faster spinning Earth mean? 3.5 billion years ago, a day on Earth was only 12 hours long. At that speed, life would have been chaotic, with extreme weather and hurricanes sweeping across the land. The faster spin would have caused water to gather around the equator, flooding areas like Indonesia and northern South America. That's a worst-case scenario, and Earth is unlikely to ever spin that fast again. If Earth keeps speeding up, it could cause big problems. By 2030, we might face a major tech meltdown. GPS relies on precise timing, and if a day becomes too short compared to the 24-hour standard, it could lead to serious issues. Satellites could lose their correct positions in the sky, making it hard to track them. If we don't fix this in time, our navigation systems could become inaccurate, throwing off all our smart technology. Fortunately, there's a simple solution. Timekeepers can add or remove what's called leap seconds to adjust for these tiny differences. They can tweak international atomic time to match up with Earth's rotation. By watching the night sky, we can monitor these small changes. That's how we know Earth is spinning faster. But it doesn't explain why, after billions of years of slowing down, the Earth is suddenly speeding up. So what's causing this? According to scientists, melting ice caps are not only causing sea levels to rise, but also making Earth spin faster. When Earth spins faster, it creates more centrifugal force. Think of a figure skater. When they spin slowly with their arms outstretched and then pull their arms in, they start to spin faster. This happens because they're bringing more mass closer to the center of their spin. A similar effect could be happening on Earth. Water has a special property. It expands when it freezes. Glaciers, ice sheets, and ice-covered mountains are like giant, towering blocks of frozen water. But what happens when they start melting quickly, as we're seeing now? When all that ice melts, the mass from the glaciers and ice sheets moves closer to the Earth's surface. As the melted ice moves toward the center of the Earth's rotation, it causes the Earth to spin faster. This meltwater is currently concentrated at the poles, which is why scientists think Earth is spinning faster than usual. But will it keep speeding up forever? Here's the tricky part. Scientists actually think this faster spin is temporary. Although Earth has been spinning faster over the past 2 years, experts believe it will eventually slow down again, returning to its long-term pattern. The reason for this slowing down has to do with the Moon. This is connected to the gravitational relationship between the Earth and the Moon. We only see one side of the Moon because it's tidally locked with Earth. As the Earth rotates, the Moon's gravity pulls on our oceans, creating tides. As Earth rotates away, the oceans move back, causing a sort of wobble in Earth's movement. This interaction between the Earth and the Moon actually slows down Earth's spin over time. As the Earth's rotation slows down, the energy lost is transferred to the Moon, causing the Moon to move further away from us. As the Moon drifts away, its gravitational pull on Earth weakens, which will slow down Earth's spin in the long run. Additionally, over time, the melted water from the polar regions might actually slow down Earth's rotation even more. Some scientists think this water will move toward the equator, further slowing Earth's spin. This process is called equatorial bulging. Imagine it as the Earth getting a bigger spare tire around its middle. This bulge already exists because of the centrifugal force from Earth's rotation, but adding more water to it isn't a good thing. The extra water around the equator means there's more mass further from the center of rotation. The equatorial bulge will grow, leading to even higher sea levels around the equator than previously expected. This could make hurricanes, typhoons, and cyclones that form near the equator more intense because there's more water vapor in the air. So, while the increased severity of storms due to the Earth spinning faster might be temporary, it's still a cause for concern. More severe storms mean more natural disasters around the world. The origin of life on Earth is one of the greatest mysteries in science. While many theories suggest that life began here on our planet, some scientists have proposed a fascinating alternative, that life, or at least the building blocks of life, may have come from space. This idea, known as panspermia, suggests that the seeds of life could have been transported across the cosmos, eventually taking root on Earth. But is there any evidence to support this theory? And if so, what does it mean for our understanding of life in the universe? Now discussing the basics of panspermia, it is a theory that suggests life, or the ingredients necessary for life, didn't originate on Earth, but was instead delivered here from outer space. The word panspermia comes from the Greek words pan, meaning all, and sperma, meaning seed. The idea is that life could be widespread throughout the universe, with tiny organisms or organic molecules traveling through space and potentially seeding life on other planets, including Earth. Before discussing the evidence supporting panspermia, we will need to first know about several forms of panspermia. So the first is something known as lithopanspermia. This theory suggests that life could have been carried to Earth on meteorites, comets, or other space debris. Microorganisms, or the building blocks of life, might have pulled a ride on these objects, surviving the harsh conditions of space. And then the second one is known as radiopanspermia. This form of panspermia proposes that microscopic life forms, such as bacteria, could be propelled across space by radiation pressure from stars. These tiny organisms might have traveled vast distances before landing on Earth. And the third one is directed panspermia. This is the most speculative form, suggesting that an advanced alien civilization might have intentionally seeded life on Earth or other planets. While panspermia remains a hypothesis, there is some evidence that scientists have discovered over the years. First one is the meteorites containing organic molecules. Scientists have found organic molecules, including amino acids, the building blocks of protein inside meteorites that have landed on Earth. One famous example is the Murchison meteorite, which fell in Australia in 1969. It contained a variety of organic compounds, including amino acids, suggesting that these essential ingredients for life could be present throughout the universe. Another evidence is extremophiles. So basically, these are microorganisms that we found on Earth, such as deep-sea hydrothermal vents, acidic hot springs, and even the vacuum of space. So maybe it suggests that life, or at least simple forms of life, could potentially survive the journey through space and the conditions found on other planets. And the third evidence is the early bombardment period. During the early history of the solar system, Earth was bombarded by comets and asteroids, a period known as the late heavy bombardment. If these space rocks carried organic molecules or microorganisms, they could have deposited them on Earth, potentially kick-starting the process of life. But some years ago, I remember the news about life that came from Mars was on the first pages. Billions of years ago, Mars had conditions that could have supported life. Evidence suggests that Mars once had liquid water on its surface, a thicker atmosphere, and a climate that was warmer than it is today. If life did exist on Mars, it's possible that microbial life forms could have been ejected from the Martian surface by powerful impacts from asteroids or comets. These impacts could have launched rocks containing microorganisms into space, some of which might have eventually found their way to Earth. This process of transferring life between planets via meteorites is a form of panspermia known as lithopanspermia. We also have some evidence suggesting Martian life could have been transported to Earth. The first is Martian meteorites on Earth. We know that rocks from Mars have made their way to Earth. Several meteorites found on Earth have been identified as coming from Mars, based on their unique chemical and isotopic signatures. These meteorites were blasted off Mars by impacts and traveled through space before landing on Earth. If these rocks contained microbial life, they could have potentially seeded life on our planet. Early Mars and early Earth had somewhat similar environments, with the presence of water, volcanic activity, and the potential for organic molecules. This similarity suggests that if life could start on Earth, it might also have started on Mars and then been transferred here. So if life can spread through space, it suggests that life could be common throughout the universe. Planets, moons, or even asteroids that are capable of supporting life might have been seeded by microorganisms or organic molecules from elsewhere. While panspermia is an exciting possibility, many scientists still believe that life began on Earth itself through a process known as abiogenesis. This is a theory that proposes that life arose naturally from non-living matter, such as simple organic compounds. This process would have occurred over millions of years. There is also some evidence suggesting about naturally accrued life on Earth. First one is the Miller-Urey experiment. In 1953, scientists Stanley Miller and Harold Urey conducted an experiment that simulated the conditions of early Earth. They found that by applying an electrical charge to a mixture of water, methane, ammonia, and hydrogen, they could produce amino acids, which are the building blocks of proteins. This experiment provided strong evidence that the basic components of life could have formed naturally on early Earth. Another strong evidence is of hydrothermal vents. Some scientists believe that life may have originated around hydrothermal vents on the ocean floor. These vents release heat and chemicals from deep within the Earth, creating an environment that could have fostered the formation of complex organic molecules. Extremophiles found around these vents today offer clues that similar conditions may have given rise to early life. Another theory suggests that life may have originated on the surface of minerals, particularly clay. Certain types of clay can attract and concentrate organic molecules, potentially providing a surface where complex chemical reactions could occur. The question of whether life on Earth arrived from space is a fascinating one that continues to confuse scientists. While the panspermia hypothesis offers a tantalizing possibility, it remains just a possibility. The evidence we have is compelling but not conclusive. Most scientists still believe that life began on Earth through natural processes, though the idea that life could be widespread in the universe and capable of traveling across the cosmos is an exciting one. The Moon is one of the largest natural satellites in our solar system, almost as big as Mercury. This size similarity raises an interesting question. How did Earth and the Moon form this way? Why are these two bodies orbiting each other? There are some fascinating facts about Earth and the Moon. For example, a space probe orbiting Mars took a picture showing Earth and the Moon from Mars' perspective. One interesting fact about the Moon is that it has very little iron in its core, unlike Earth, which has a lot of iron in its core, giving it a magnetic field. This difference is confusing because if the Moon formed in the same region as Earth, why does Earth have so much iron in its core while the Moon has so little? Another curious aspect is the amount of spin in the Earth-Moon system. The Moon orbits Earth quickly, and both Earth and the Moon rotate. In physics, spin, or angular momentum, doesn't just appear out of nowhere, it has to come from somewhere. So when we see the Earth and Moon spinning rapidly, and the Moon orbiting Earth quickly, there must be an explanation for that. Why is there so much spin in the Earth-Moon system? One of the greatest achievements in human history was when we landed on the Moon in 1969. During this mission, we collected moon rocks and brought them back to Earth. Scientists found that these moon rocks are very similar in composition to rocks on Earth. This suggests that the Moon and Earth might have come from the same source. By studying the decay of radioactive elements in the moon rocks, scientists can determine their age. These rocks seem to be about 30 to 50 million years younger than Earth. While this difference might not seem significant, since Earth is about 4.5 billion years old, it does indicate that the Moon formed slightly after Earth. Another interesting fact involves isotopes, which are different forms of the same element. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The same concept applies to oxygen. The ratio of these different forms of oxygen can be measured very accurately. In various parts of the solar system, these ratios differ depending on how close or far a planet formed from the Sun. However, on Earth and the Moon, these ratios are very similar, indicating a shared origin. So we have a bit of a mystery here. The Moon is slightly younger than Earth, spins quickly, is made of similar materials, but has very little iron. What's the explanation for that? There is a widely accepted theory that explains all these things. Some people question it, which shows how science works. It's not 100% proven or accepted, but it makes sense based on the evidence. Scientists have several theories about how the Earth and Moon formed. One of the most widely accepted theories is the giant impact hypothesis. The most widely accepted theory suggests that about 50 million years after Earth formed, another planet, about the size of Mars, came very close to Earth. This planet collided with Earth, hitting it at an angle and knocking off a lot of debris without reaching Earth's core. Since heavy elements like iron sink to the center when planets form, most of Earth's iron was already in its core, so the material that was knocked off had very little iron. This collision also caused a lot of spin, similar to how kicking a football on the side makes it spin and curve. This explains why the Earth-Moon system has so much spin. The Moon formed from the debris of this collision, which is why it's made of similar materials and isotopes as Earth. Because the collision happened 50 million years after Earth formed, it also explains why the Moon's rocks are slightly younger than Earth's. It seems the Moon formed from a planetary collision about 4.5 billion years ago. All the evidence supports this idea, especially the 4 key observations about Earth and the Moon. Plus, when we went to the Moon and collected samples, the lab analysis backed up the theory even more. This collision not only formed the Moon, but also played a big role in shaping Earth's future. The impact likely tilted Earth's axis, which is why we have seasons. Without this tilt, our planet might not have the climate patterns that support diverse life forms. The Moon also helps stabilize Earth's rotation, preventing extreme tilts over long periods, which would have drastic effects on our environment. Additionally, the gravitational interaction between Earth and the Moon creates tides, which have influenced the evolution of life on Earth. The regular rise and fall of ocean levels have affected coastal ecosystems and human activities for thousands of years. Interestingly, the Moon is gradually moving away from Earth. Measurements show that the Moon drifts about 3.8 centimeters farther from Earth each year. This slow separation affects Earth's rotation and the length of our days. Millions of years ago, days were shorter, and as the Moon continues to move away, days on Earth will gradually become longer. While the giant impact hypothesis is the most widely accepted theory, there are other interesting theories. One is the fission theory, which suggests that the Moon was once part of Earth but separated due to Earth's rapid rotation in its early days. However, this theory struggles to explain the Moon's current orbit and how such a separation could happen. Another theory is the capture theory. According to this idea, the Moon formed elsewhere in the solar system and was later captured by Earth's gravity. This could explain why the Moon has a different composition from Earth. However, capturing such a large body without it breaking apart or escaping again seems highly unlikely. Despite these theories, the exact process of the Moon's formation continues to be a topic of scientific investigation and debate. The unique relationship between Earth and the Moon has a significant impact on life here. The Moon's gravitational pull creates tides, which have influenced the evolution of life and the development of human civilizations. The regular rise and fall of ocean levels have affected coastal ecosystems and human activities for thousands of years. The Earth-Moon system is a fascinating subject of study, providing insights into the formation and evolution of planetary bodies. The differences in composition, the shared angular momentum, and the ongoing relationship between Earth and its only natural satellite all tell a complex and intriguing story about our place in the cosmos. Uranus, the 7th planet from the Sun, is a unique world in our solar system. One of its most unusual features is its extreme axial tilt. Unlike most planets that rotate with their axes more or less straight up and down, Uranus is tilted at an angle of about 98 degrees. This means that Uranus essentially rolls around the Sun on its side, with its poles taking turns facing the Sun directly. Let's explore the details of this strange tilt and the mystery surrounding it. The odd tilt of Uranus is believed to be the result of a massive impact that happened billions of years ago, not long after the planet formed. According to this theory, a huge object, possibly as large as Earth or even bigger, collided with Uranus, causing it to tip over onto its side. This dramatic event likely changed Uranus' rotation and orbit, leading to the extreme tilt we see today. While this theory is widely accepted, the exact details of the impact and the object that caused it are still unknown. Some scientists suggest that it wasn't just one big impact, but a series of smaller collisions that gradually tilted Uranus to its current extreme angle. These smaller impacts could have slowly changed the planet's axis without destroying it or dramatically altering its overall structure. Uranus' extreme tilt has a big effect on the planet's seasons and climate. On Earth, we experience relatively mild seasonal changes because our planet's tilt is only about 23.5 degrees. But with a 98-degree tilt, Uranus's poles each get about 42 years of continuous sunlight, followed by 42 years of darkness, as it takes 84 Earth years for Uranus to complete one orbit around the Sun. This creates some of the most extreme seasonal variations in the solar system. During its long summer, one pole of Uranus stays in continuous sunlight, while the other side remains in darkness. As Uranus continues its orbit, this gradually reverses, with the opposite pole experiencing summer. This unique tilt leads to extreme temperature changes and unusual weather patterns. The planet's atmosphere, made mostly of hydrogen, helium, and methane, shows dynamic and complex behavior because of these extreme seasonal changes. Uranus's atmosphere is another fascinating feature of the planet. Its blue-green color comes from the methane in the atmosphere, which absorbs red light and reflects blue and green light, giving Uranus its distinctive hue. The atmosphere also has incredibly fast winds that can reach speeds of up to 560 miles per hour. These winds, combined with the planet's extreme tilt, create turbulent weather and dramatic cloud formations. One of the most interesting aspects of Uranus' atmosphere is the presence of dark spots, similar to Jupiter's Great Red Spot. These dark spots are believed to be storms or vortices, and their appearance can change over time. Observations from the Hubble Space Telescope and other instruments have helped scientists study these features, offering valuable insights into the dynamics of Uranus's atmosphere. Uranus's unusual tilt also affects its magnetic field. Unlike Earth, where the magnetic field is roughly aligned with the rotational axis, Uranus's magnetic field is tilted about 59 degrees relative to its axis. This means that the magnetic field is off-center and more complex than Earth's. Scientists think that Uranus's magnetic field is generated by a layer of ionic slush in the planet's interior, made up of water, ammonia, and methane. This layer, combined with the planet's rotation, creates Uranus's unusual magnetic field. Studying Uranus's magnetic field gives scientists important clues about the planet's interior structure. They believe that Uranus has a core made of rock and metal, surrounded by a thick layer of icy materials. The outermost layer consists of hydrogen and helium gas, similar to Jupiter and Saturn. Understanding the magnetic field helps researchers create models of Uranus' interior and its formation history. In addition to its tilt and magnetic field, Uranus has a system of rings and moons that make it unique. The rings of Uranus were discovered in 1977 and are much darker and narrower than Saturn's rings. These rings are made mostly of large particles and are believed to be relatively young, possibly formed from debris of shattered moons or captured objects. Uranus has 27 known moons, with the largest being Titania, Oberon, Umbriel, Ariel, and Miranda. These moons are named after characters from the works of William Shakespeare and Alexander Pope. Each moon has its own unique features and geology. For example, Miranda, the innermost of the large moons, has a very diverse surface with deep canyons, ridges, and areas that seem to have been reshaped by geological processes. This diversity suggests a complex history of internal activity and resurfacing. The unique characteristics of Uranus have made it a topic of great interest for planetary scientists. Despite its fascinating features, Uranus has been relatively underexplored. The only spacecraft to visit Uranus was Voyager 2, which flew by the planet in 1986. Voyager 2 provided valuable data and images, but there is still much to learn about this distant world. There is also a hypothesis that suggests the influence of a large moon or multiple moons that could have exerted strong enough gravitational forces to tilt Uranus over time. However, the current moons of Uranus are relatively small compared to the planet, making this less likely than the giant impact hypothesis. Studying Uranus also helps us understand more about the solar system as a whole. By learning more about Uranus, scientists can gain insights into how planets form and evolve. Uranus is considered an ice giant because it has more icy materials compared to the gas giants Jupiter and Saturn. Studying ice giants like Uranus and Neptune can help researchers understand the different types of planets and the conditions that lead to their formation. In recent years, there has been growing interest in sending a dedicated mission to Uranus. Such a mission could include an orbiter and possibly a probe to study the planet's atmosphere in detail. By conducting long-term observations, scientists could monitor seasonal changes, atmospheric dynamics, and variations in the magnetic field. Additionally, close-up studies of Uranus' rings and moons could provide new insights into their composition and history. In 1950, a famous physicist, Enrico Fermi, asked a simple yet important question during a lunch with his colleagues. If our galaxy is so big, where are all the advanced alien civilizations? This question is now known as the Fermi paradox. The paradox comes from the fact that with around 400 billion stars in our galaxy, it seems likely that some planets should have intelligent life. If that's true, these civilizations would have had plenty of time to explore and maybe even visit Earth. But we haven't found any clear evidence that this has happened. To explain why we haven't seen any signs of extraterrestrial civilizations, despite the high chance that they exist, several theories have been proposed. First one, if traveling between solar systems might be extremely costly and require huge amounts of resources. For example, sending a spaceship to even the closest star would take a massive amount of energy and money, making it impractical. Another one is limited expansion, where even if a civilization starts exploring and colonizing other planets, it might be hard to keep expanding across generations. The effort needed to keep moving from one star system to another might be too difficult to maintain. Another idea suggests that it's possible that the galaxy is full of activity in other areas, but we're just in a quiet part where not much is happening. Another idea suggests that Earth is like a zoo or nature reserve, where aliens are watching us from a distance, making sure we don't know they exist. To understand where the Fermi paradox comes from, we need to look at two key ideas. The first is the Drake equation, created by Frank Drake, a major figure in the search for alien life. This equation suggests there could be thousands of civilizations in our galaxy that are capable of sending us signals. The second idea is the Fermi paradox itself, which asks why we haven't found any clear signs of intelligent aliens, like evidence of space travel between stars. The name Fermi paradox is a bit misleading. It was named after Enrico Fermi, but he didn't actually create this theory. Still, the idea is important when discussing the possibility of alien life and has influenced research funding. For example, the Fermi paradox influenced Senator William Proxmire's decision to stop funding NASA's SETI program in 1981. Although Carl Sagan managed to bring the program back briefly, It was shut down again in 1993 by Senator Richard Bryan. However, the search for alien life hasn't stopped. While NASA doesn't fund SETI like it used to, research continues through other sources. The SETI Institute, a private non-profit organization, carries on the work. The institute partners with universities, companies, and even government agencies, including NASA, to keep searching for signs of extraterrestrial life. Interestingly, the term Fermi paradox didn't actually come from Fermi himself. What we know about his thoughts comes from a 1950 lunch in Los Alamos, as remembered by physicist Eric Jones, who interviewed 3 of Fermi's colleagues. During this lunch, Fermi wondered about space travel. This conversation eventually led to what we now call the Fermi paradox. According to Teller and York, Fermi was more interested in whether traveling between stars was possible, not necessarily whether aliens exist. The Fermi paradox is usually understood to mean that there's no evidence of extraterrestrial life, but this wasn't Fermi's main concern. His doubts were more about whether space travel was possible, which made sense in 1950 when rockets couldn't even reach orbit, let alone other planets or stars. The idea that no aliens on Earth means no aliens anywhere was first introduced by astronomer Michael Hart in 1975, not by Fermi. Michael Hart argued that if intelligent aliens existed, they should have already colonized the Milky Way. Since we haven't seen any evidence of them on Earth, he suggested that humans might be the only intelligent beings in our galaxy. He even thought that searching for alien civilizations might be a waste of resources. However, many people disagree with his conclusion. They point out that space travel might be impossible. Aliens might choose not to colonize other planets, or they might have visited Earth long before humans existed, leaving no traces. Despite these criticisms, Hart's idea is still widely discussed when talking about extraterrestrial life. In 1980, physicist Frank Tipler expanded on Hart's ideas by considering the huge resources needed to explore billions of stars. Tipler suggested the idea of self-replicating robots with human-like intelligence. These robots could be sent to a nearby star, use local resources to create copies of themselves, and those copies could continue spreading across the galaxy. Tipler concluded that since we haven't found any of these advanced robots on Earth, it could mean we're the only intelligent civilization not just in the Milky Way, but in the entire universe. This idea is bold, based only on the fact that we haven't encountered aliens yet. What we now call the Fermi paradox mostly comes from the ideas of Hart and Tipler, but over time, their theories have been mixed up with Fermi's original question, leading to some confusion about where the paradox actually came from. This confusion likely started in 1977 when physicist David Stephenson used the term \Fermi paradox in a publication, presenting Hart's theory as a response to Fermi's question. A more accurate name for this idea could be the Hart-Tipler argument against the existence of technological extraterrestrials. Although this name isn't as catchy as the wrongly attributed Fermi paradox, it would better recognize the true originators of the concept. The search for alien life is still a major focus for scientists. The James Webb Space Telescope is giving us amazing new images and data, while Mars rovers are studying the planet up close. There are also plans for future missions to explore the farthest parts of our solar system. The question of whether we are alone in the universe remains unanswered, and until we find out, the search for extraterrestrial life will stay a top priority for humanity. Scientists have developed different ways to look for life beyond Earth. The key area of research is studying exoplanets, which are planets that orbit stars outside our solar system. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, some of which are in the habitable zone, where conditions might allow life. The habitable zone is the region around a star where temperatures could allow liquid water to exist. Since liquid water is essential for life as we know it, these exoplanets are top candidates for further study. For life to exist, certain ingredients are needed. Besides liquid water, life requires key elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements are the building blocks of organic molecules, which make up all known life forms. Interestingly, these elements are common in the universe. They've been found in interstellar clouds, comets, and even on other planets and moons in our solar system. Scientists are also searching for biosignatures, which are signs of life that can be detected from far away. Biosignatures could include specific gases in a planet's atmosphere, like oxygen or methane, that might indicate the presence of life processes. Another interesting area of research is the search for technosignatures, which are signs of advanced civilizations. This includes looking for radio signals, laser pulses, or other kinds of technology that might suggest intelligent life. Projects like SETI have been scanning the skies for decades, hoping to pick up a signal from an alien civilization. While searching for life outside Earth, scientists are also exploring the possibility of life within our own solar system. Moons like Europa and Enceladus, which have oceans beneath their icy surfaces, are especially interesting. These oceans could have the right conditions for life, shielded from space by a thick layer of ice. As technology improves, our ability to search for extraterrestrial life will continue to get better. New telescopes, space missions, and artificial intelligence will increase our chances of detecting and studying possible signs of life. We've found over 4,000 planets orbiting other stars, and we now know that almost every star has at least one planet. About 1/5 of these stars have planets the size of Earth orbiting them. With around 100 billion stars in the Milky Way, there are likely billions of Earth-sized planets out there. It seems unlikely that only one of these planets has life. Given the huge number of Earth-like planets just in our Milky Way, we have to ask, are we really alone in the galaxy? The Hubble Space Telescope has shown us about 100 billion galaxies. Each of these galaxies has around 100 billion stars. Altogether, that's roughly 10,000 billion stars in the visible universe, a number that's hard to even imagine. Given how big the universe is, the chances of life existing somewhere else seem pretty high. Think about how vast our universe is, filled with an enormous number of stars. Even in our own Milky Way, with its 100 to 400 billion stars, it seems unlikely that Earth is the only place with intelligent life. The huge number of stars suggests that life somewhere else in the universe is almost certain. Frank Drake was a scientist who tried to figure out how many civilizations might exist in our galaxy that we could detect. He came up with a series of questions that, when combined, give us an estimate. This set of questions became known as the Drake equation, which helps predict the number of detectable civilizations in the Milky Way. For over 60 years, the Drake equation has been our main tool for estimating how many civilizations could be out there, with numbers ranging from 1,000 to 100 million planets hosting civilizations. In the Drake equation, R is the rate at which new stars are formed in our galaxy each year. Then, E is the percentage of these stars that have planets. Next, we look at Ne, which estimates how many of these planets are in the habitable zone, where life could exist. This part is still mostly unknown since we don't know much about planets beyond our solar system. The number 4 tries to figure out how many of these planets actually have life. Then Phi estimates how many of those planets develop intelligent life. When Frank Drake created his equation, he focused on radio astronomy. He wanted to know how likely it was that alien civilizations were sending signals we could pick up with our technology. That is represented by phi in his equation. Back in the 1960s, many scientists believed radio waves were the most likely way advanced aliens would communicate. Earth has been sending radio signals into space for nearly 100 years, reaching stars within an 80 light-year radius. But a big question remains. Would aliens in other parts of the universe still use radio waves, or would they see them as outdated, like how we think of smoke signals? The last part of the Drake equation, L, tries to estimate how long a civilization might be detectable in our galaxy. Frank Drake, the scientist behind this equation, was worried that even if a society developed advanced technology, their signals might only last for a short time. So, even if civilizations last for thousands of years, we might only catch a brief signal from them. When Drake first did his calculations in 1961, he estimated there could be 4 to 10 detectable civilizations in our galaxy. But with today's scientific updates, the number is much lower. The new estimate for N, the number of detectable civilizations, is about 0.00127. This means that in every 100,000 years of our galaxy's history, only about 127 civilizations might become detectable. Drake's original belief that there could be around 10,000 civilizations in the Milky Way suggests a busy galaxy. But the difficulty of finding even one civilization among 100 billion stars shows just how hard the task is. To make any real claims about how common or rare these civilizations are, astronomers might need to study 10 million stars. This shows the enormous effort required. We still don't know how many alien civilizations could be out there. Estimates range from just a few to as many as 100 million in the Milky Way alone. But some think we might be the only advanced civilization in our galaxy. That doesn't mean we're alone in the entire universe, which is incredibly vast. The observable universe spans about 92 billion light-years and has anywhere between 100 billion and a trillion galaxies, each with around 100 billion stars. So, there's a good chance that intelligent life exists somewhere, just maybe not in our Milky Way. Over Earth's history, more than 10 billion species have existed, but none have shown the intelligence, curiosity, and ability to create complex tools like humans. Even smart animals like whales and dolphins don't seem to think deeply or make complex tools. Humans have only been around for a few 100,000 years, so for most of Earth's history, an alien looking at our planet wouldn't see any advanced technology or signs of high intelligence. It's also unclear if being so smart is good for us in the long run. While our intelligence has made life better for many, it has also brought us close to self-destruction. Recently, astronomers have been trying to get better estimates of how many alien civilizations might be in our galaxy. They're focusing on two big questions: how likely it is for life to start on Earth-like planets from non-living materials, and what the chances are that this life becomes intelligent. Even with these estimates, there's still a lot of disagreement. Some scientists argue that with so many Earth-like planets, we can't be the only ones. Others want solid proof and ask, if there are so many civilizations out there, why haven't we found any evidence of them? This is the big question behind what's known as the Fermi paradox. If alien life is common, where is everybody? The search for extraterrestrial intelligence has been actively scanning the sky, but we've only looked a few hundred light-years away, which is just a tiny part of our galaxy. If the galaxy was full of life, especially advanced life, some of it would be much more developed than us. Stars in our galaxy went through processes billions of years ago that created the elements needed for Earth-like planets. So there could be civilizations out there that are billions of years more advanced than us. Considering how fast human technology has developed in just a few hundred years, imagine what a civilization could achieve in thousands or even millions of years. Such civilizations could potentially travel between stars and colonize the galaxy. In theory, they could fill the entire galaxy in just a few million years. If they existed, we might expect them to have reached us by now. On the night of July 15, 1977, astronomer Jerry Ehman, a volunteer for the search for extraterrestrial life, was scanning radio signals when something surprising happened. He picked up a strong and unusual signal. This signal lasted for 72 seconds, was 30 times louder than the usual background noise, and seemed to come from the direction of the constellation Sagittarius. The data was translated by a computer into a series of letters and numbers, resulting in the sequence 6EQJ5. When Jerry saw the printout the next day, he was so amazed that he circled the sequence and wrote "wow" next to it. That's how the signal got its name, the wow signal. Experts concluded that the signal source was broadcasting in a regular pattern, like the rotating beam of a lighthouse. It's as if we only picked up the signal when it was directly aimed at us and then lost it as it turned away. Despite all the monitoring and analysis done since then, the wow signal remains one of the strongest pieces of evidence, and its origins continue to be widely debated and researched. Whether it was actually a message from aliens or not is still a mystery. Scientists believe that what we detected as the wow signal might not have been the whole transmission. Instead, it could have been part of a repeating signal. To understand why we didn't catch the entire thing, we need to look at how the telescope worked. The wow signal was picked up by the Big Ear telescope at Ohio State University, which was built specifically to search for extraterrestrial signals. The telescope was huge, about the size of 3 football fields, with a large mirror that captured signals and bounced them towards smaller mirrors. These mirrors then directed the signals to 2 receivers for analysis. However, the way the Big Ear telescope was built made it difficult to consistently pick up the signal. After it first detected the wow signal, there was a few-minute delay before the second receiver could check the same area of space. By that time, the signal was gone. This gap in detection is a big hurdle when trying to confirm where the signal came from. The design and operation of the Big Ear telescope show how the structure of such equipment can affect our ability to confirm signals. If the telescope could have monitored the same spot continuously or quickly revisited it, scientists might have been able to see more signals from the same region in the Sagittarius constellation. This could have provided clearer evidence of where the signal was coming from. The limitation here shows just how important the telescope's design is when it comes to searching for signals from other civilizations. The Big Ear wasn't like traditional telescopes that use mirrors to capture light. It was a radio telescope that used wireframe capture dishes to detect radio frequencies, which are invisible to our eyes. Unlike modern telescopes that can turn in all directions to scan the sky, Big Ear could only tilt its reflector up and down, limiting it to observing a narrow strip of the sky at a time. This design was chosen because it was simpler and cheaper to build than more advanced systems. To overcome this limitation, the designers found a clever way to increase its range. By relying on the Earth's rotation to move the telescope left and right and adjusting the reflector to cover different angles, Big Ear could eventually observe any point in the sky. This use of the Earth's natural movement was a smart way to make the most out of the telescope's limited mobility, allowing it to cover more ground despite its restrictions. But there was still a downside. Because the telescope relied on the Earth's rotation, it couldn't keep track of the same spot in the sky for very long. This means it might have missed additional signals coming from that region. Picture an entire orchestra of signals being sent from that spot after the wow signal, but Big Ear only caught a brief note from what could have been a much larger broadcast. The challenges faced by SETI in their search for alien life are largely due to the vastness of space and limited resources. They can't dedicate a single telescope to watching one spot for years, hoping for a response. Instead, they scan large areas of the sky, moving from place to place to increase their chances of picking up a signal, even if only for a moment. This approach is like casting a wide net in different locations rather than waiting in one spot. It's a practical strategy, given the uncertainty of where and when a signal might show up. The search for alien signals isn't random, even though it may seem that way. Unlike fish, which can be attracted or scared off by our actions, alien signals aren't influenced by our attempts to find them. While sweeping a telescope across the sky might seem like a guessing game, it's the best approach considering the vastness of space and the uncertainty of where a signal might be. However, this approach has its challenges, especially when it comes to following up on strange signals like the WOW signal. Over the years, radio telescopes have picked up several mysterious, short-lived signals similar to the WOW signal, quick bursts of radio waves that we still don't fully understand. The main problem is that without continuous observation and dedicated studies, these signals remain mysterious and often go unnoticed. Without proper follow-up, we may miss out on important data, leaving us with only guesses about where these signals come from. This brings up an important point. The reason we haven't found signs of intelligent extraterrestrial life could be due to how we're searching for it. Of course, this is just one possible explanation. In this discussion, we've covered some of the technical challenges in detecting alien life. But there are also many other theories that are more speculative and touch on deeper questions about our place in the universe and the nature of other civilizations. These theories open up interesting possibilities about what life beyond Earth could be like. The question of whether aliens are out there watching us from the stars is both exciting and complicated. The vast number of stars and galaxies in the universe suggests that the conditions for life, including intelligent life, could be common far beyond Earth. If even a small percentage of planets around these stars can support life, then life might be widespread in the cosmos. There are many reasons why we haven't made contact with other civilizations yet. One reason could be the vast distances between stars, making communication and travel across space extremely difficult. Another reason might be timing. Civilizations could rise and fall at different times, missing the chance to connect with each other. Another important factor is the way communication happens. Advanced civilizations might use technologies or methods that we don't yet understand or can't detect. It's also possible that they choose not to contact us, perhaps observing us from a distance, like how we study less developed species on Earth.